Okay, I think it's time to start. So let us welcome Nathan Kutz, who will talk today about deep learning for the discovery of parsimonious physics models. And before he can start his talk, I will read his short bio so you get some details about our speaker today. And Nathan Kutz is the Chasuko Endo and Robert Gold Professor of Applied Mathematics at University of Washington, having served as the chair of the department from 2007 to 2015. He received his bachelor degree in physics and mathematics from the University of Washington and the PhD in applied mathematics from Northwestern University. He was a postdoc in the Applied and Computational Mathematics program at Princeton University before taking his current faculty position. And he has a wide range of interests, including neuroscience to fluid dynamics, where he integrates machine learning with dynamical systems and control. So let us welcome Nathan. And yeah, we're looking forward to your talk.
Great. Thank you guys so much for having me. And well, I hope you're all recovering from IDA. I know that was probably a tough week for all of you. So feel free to put things up in the chat. I have it open so I can hopefully read anything that you want to ask as we go along. And I'm just going to give you some perspectives on how we think about some deep learning, how deep learning can be applied to really the engineering and physical sciences and building models for data. All this work, really, almost everything I'm going to highlight here is with Steve Brunton, who is a colleague of mine in mechanical engineering. And what I'm really going to do is highlight the work of the students and postdocs that we have co-mentored. They're really the stars of the shows, and you'll see them along as we go along on different pieces of work. And so really, this is a group effort of a lot of people, a lot of really talented students and postdocs who have produced this overall perspective that you'll see here. So the thing that we're going to really focus in on is this idea of thinking about using data to discover both coordinates and dynamics. I'm going to get quite a bit into this as we go, but really this is going to be the whole strategy in this talk, which is how can I take data, learn how to embed it in an advantageous coordinate system or a latent representation, and then build models in there and then come back out into my original measurement space, okay, of what I was actually measuring. And we're going to do this really, I'm already starting to frame this in terms of neural nets. So you see this here, we're going to learn coordinates through neural networks, through deep learning. And so it's going to be a targeted use of neural nets. We're not going to really use neural nets end to end, just learn a black box, anything. We're going to try to constrain the use of neural nets so that at the end of it, we have some interpretability and explainability available to us to understand what the data is telling us. So, by the way, this idea of coordinates and dynamics certainly is not new. It's kind of what we've been doing for most of the time in mathematical physics and advanced engineering mathematics, which is we often learn coordinate transformations. Some of these coordinate transformations are special functions like Bessel, Hermite, Laguerre. This is these canonical things of mathematical physics, but also coordinate transformations like Laplace transforms, Fourier transforms. In other words, move your representation into some advantageous framework where you can take advantage of a better modeling paradigm. We do this with special functions, expert knowledge, and more recently, we've been doing this through SVD, singular value decomposition-based methods. So oftentimes these go under names like proper orthogonal decomposition, principal component analysis, empirical orthogonal functions, Holt-Link transformation, lots of different names for the same thing, which is the singular value decomposition. In other words, look for the dominant correlated structure, project into that low rank subspace. It's a linear projection. And more recently, people are interested, like us, in neural networks, which allow you, instead of a linear projection, I can build a nonlinear mapping from my measurement space into this latent variable representation. By the way, once we get it into this coordinate system, what do we do with it? Well, now we want to model what happens. Oftentimes, at least what we're interested in, is modeling spatial temporal dynamics. And so we want to model what goes on inside of this new latent representation. And there's a lot of ways to handle the time courses or the time dynamics, time series that are here. You can use standard statistical methods like ARIMA models, like these are autoregressive moving average models, or things like dynamic mode decomposition and Koopman operators. I'll talk about some of those. I'm also going to talk about SINDy, which is this sparse regression framework for discovering governing equations. You can embed things if you're in a dynamical systems mind frame, you can embed them in normal forms, or you could just use a standard neural network in the time series itself. Things like LSTMs, recurrent neural networks, GRUs, echo state networks, lots of different ways to construct models in this temporal representation. And so we want to pair these. We want to think about, how do I discover coordinates and dynamics jointly? That's what we're really going after here. So, I mean, the first concept I want to bring to the forefront of our minds is, what does it mean to have a good coordinate system? So this is like one of the most important physics problems ever for us was, celestial mechanics for this dominated for millennia our scientific thought, which is, if I look at the trajectory of the planets, how do you explain this retrograde motion that you see here in the night sky of Mars, or over here of this is Saturn? So how do you explain this? What is the physics of this? In fact, this is sort of the oldest and grandest of physics problems, in my view, which is we want to understand celestial mechanics. And so what was the progression of really achieving this understanding? Well, the first really critical piece of theory came during the Ptolemaic reign in Egypt. So it was Alexandria, Egypt, 2nd century AD, where Ptolemy proposed what's called the doctrine of the perfect circle. One way to think about it is circles on circles. So you think about this as, the trajectory is it's on a circle, but then rotating on another circle, and by composing these trajectories of circles, you could actually do a pretty great job of predicting the future trajectory of the planets. And so it was a highly successful theory. It's like the Roman Empire of theories. It lasted for a millennia and a half before finally being taken down. In fact, here's this nice medieval or Renaissance painting of this, of the theory of the perfect circle, where Earth was the center, and then you would map these stars out in these circles. The one way to think about this, by the way, this is like the earliest version of a Fourier transform. Decompose these planetary motions into a set of frequencies, in other words, oscillations or circle orbits. So this is a really nice concept that goes back a long ways. What supplanted it was finally really the push from right at the beginning of the scientific revolution. Some would argue that this was, in fact, the genesis of the scientific revolution was people like Galileo and Kepler and Copernicus, who proposed this radical notion that, in fact, maybe the sun was the center of our solar system, and that the planets went around the sun. The heliocentric model is very different in the sense that now it easily explains the retrograde motion as just simply an observer being in some sense, the wrong coordinate system. But the important thing also that came from this was not just that we got the coordinate system right, finally, at the late 1500s, 1600s, but that this set up the framework 100 years later for Newton to place his famous F=ma models for gravitation on this system, like the 1/√² of the distance for gravitation. So this actually transformed physics, right? We needed the right coordinate system to build the F=ma model. What's interesting about this is that, of course, that was a great model until the early 20th century. We started getting in late 1900s, we started getting enough great measurements that we realized that this F=ma model wasn't quite predicting everything as it should. At first, they thought they were missing a planet, but it turns out that, in fact, the conundrum was solved by Einstein in proposing the fact that gravitation actually warps local spacetime, which brought on the theory of general relativity, which is in some sense an improvement to the F=ma model. And surely there will be another person to the right of Einstein. Once we get better and better measurements, we'll be able to refine these models of gravitation as we go along. So there's a really beautiful history here about thinking about coordinates and dynamics together. There's also something more interesting here too in the works of Kepler versus Newton. And what I mean by this is Kepler actually had, Kepler's laws. He had predicted these elliptical orbits. He had written them down. In fact, those elliptic orbits were the solutions to Newton's F equals ma. So why do we celebrate Newton so much? In many ways, much more than we do Kepler, because in fact, all of Newton's solutions were Kepler's. The reason we celebrate Newton more in many ways, and this is just my opinion, is that once you have F equals ma, you truly have a model which allows you to extrapolate. Kepler did a curve fit of these parabolas to the data he had. Newton, with F equals ma, you can do something transformative. You could imagine launching a rocket to the moon and bringing it back. This is outside the purview of Kepler, who could only do fitting to the data, where Newton could actually extrapolate to places where nobody had ever collected data and still have an accurate model representation there because he had the governing equations. And so if we look at what we're doing here in modern machine learning, I want to bring these two things together here because in fact, let me show you these two videos here. The top is a robot from Boston Dynamics. This is from earlier in the year released, and you can see these robotics are quite remarkable about what robots can do in terms of their athletic achievements. And then the bottom is a self-driving car. In the self-driving car, you can see, can navigate complicated environments. It can go through places where you have work being done. And what I like to think of is these two represent, in some sense, the legacy of Newton and Kepler both. Because in the top one, the robot, those models are completely imbued with physics. In other words, those robots have F equals ma. They know about their center of mass, their momentum, their angular momentum. These are really critical quantities for the robot to actually be able to navigate its environment. Whereas in the bottom, the self-driving car, it is a bank of sensors with massive amounts of labeled data. And so it doesn't know any physics. It just simply says, here are my rules, here are my labels, and then I can navigate any environment. The bottom is an interpolation strategy. The top is more of an extrapolation strategy. And so where I'm going to play with today is mostly being in this top type of model, which is I really want to be able to take these machine learning, deep learning paradigms and do physics with them. Okay, so let's an intro there, and I want to get us right into then thinking a little bit about what's the mathematical construct we have to think about with this. So here's how to think about this. This is the mathematical framework. It's pretty simple, really. What we're going to do is we're going to say that the data we collect comes from some dynamical system, dx dt equals f. Okay. By the way, I don't know what f is necessarily here. So the idea here is going to see, I'm going to have a measurement of this system, and the measurement is actually y, which isn't necessarily directly measuring x. I'm measuring x through some measurement model h. There are noise in the system. And so my job here is to say, can I, from measurements alone of my system, discover h, discover f? If I can discover f, that's the governing equations. If I discover h, it tells me how to map my measurements to my actual state space. I want to understand my parametrizations. And so this is kind of the goal of what we want to do in data-driven discovery with these methods. Now, this is an ill-posed problem. In other words, essentially the way I've posed it, which is take measurements and discover f and h and x, you can't do it. It's terribly ill-conditioned and ill-posed. So how are we going to go about solving this? Well, the one thing you learn in optimization is that, well, if you have ill-posed problems, by the way, when I was in grad school, if you had an ill-posed problem, you moved on, right? You said, okay, I can't solve that. Let me go solve something else. And then as I got into the data science, like, wait a minute, if it's ill-posed, all you have to do is add regularizers or constraints. In other words, out of a space of an infinite number of possibilities of solutions, by imposing constraints, I start to narrow down the space of solutions until I get something that's actually well posed in nature. So what are we going to actually impose here for constraints? So what we're going to go for is we're going to use really old ideas all the way back to William of Ockham in the 1200s. And this is idea of interpretability and parsimony. So Ockham was the first to really suggest this idea of nominal models, use as few terms as possible to explain it and no more, right? And that's kind of what we want to go after here. And in fact, this has been reinvented over and over and over again. I put Pareto up here, Wilfredo Pareto, because we often talk about a Pareto frontier of solutions, and Pareto has his name attached also to this concept, just like Occam did. So in some view, what I think is that physics, that the ultimate physics regularization is around this idea of parsimony, a small representation of the solution, which then is going to allow us to do quite a bit of heavy lifting because we've imposed this really restrictive regularization. So that's the main, essentially, regularization I'm going to impose on this modeling paradigm right here. So the first thing we're going to do is we're going to build linear models. So we're going to say, I don't know what F is, but what I'm going to do, since I can discover a mapping from my measurements to some representation X, what I want to do is say, and I want to discover some representation X for the dynamics where I'm going to constrain the dynamics to be linear. Now, the reason you want linear models is they're easy to solve, right? So one thing that we know have a lot of good theory with, especially if you look at most of mathematical physics and also advanced engineering mathematics, almost everything revolves around linear models. And so what I want to show you is, in fact, you can start to think about how would I embed nonlinear models in a linear space. And so this is this idea of Koopman theory. So Koopman theory has really taken a big rise in the last decade, in large part to the fact that we have now computational ways to actually compute what's called a Koopman operator. And let me give you an example of this. So the example here is a simple 2x2 ODE. It's nonlinear. And so what I want to do with this is say, well, it's nonlinear, so I could always sketch the phase planes and run it numerically. But notice that if I change to a new coordinate system, y1, y2, y3, which are defined by x1, x2, x1 squared, then in this coordinate system, the system is completely linear, which means I write down an analytic solution and I'm done. I don't have to solve anything computationally. I have a closed form solution. So this here gives you a very simple example of how to build a Koopman operator. And that's exactly what we want to do now in some of these systems. So one way that we've been able to achieve this is using what's called the dynamic mode decomposition. And this dynamic mode decomposition was a way to use a best approximation of a linear model. So you have a nonlinear dynamics, and very rarely can you write the closed form solution like I just gave you, but you can approximate some linear operator. So this is the way this works. You measure a complex system, which generically is nonlinear. You take data matrices X and X prime. The difference between these is every column of X and X prime is advanced delta T in time. So I have two data matrices, a set of snapshots, and all those snapshots advance delta T. And what I'm really looking for in those, if I use those data matrices, dynamic mode decomposition then says, let me look for a linear operator that takes me from X to X prime. So in other words, what's the best linear operator that moves me delta T into the future, but for all these snapshots I have, right? So in other words, I have to figure out, like if I have 10 snapshots, I want one operator that does the best job of fitting through all 10 snapshots. So that's just a least square regression, and that's a dynamic mode decomposition model. What Koopman also allows you to do, though, is instead of working with the original data you collected, you can work with functions of the data. In other words, you can augment your observable space by saying, I want to look at what I collected, that variable x squared, x cubed, sine x. I can make up a lot of different observables here. And now once I've built that augmented observable matrix, then I do this linear regression on this augmented space. So that's typically let's say, the Koopman route to computing a Koopman operator or a DMD model for Koopman. But what we want to focus on is deep learning. And so what we're going to really focus here on is say, I want to take this process of trying to learn this representation by actually just training a neural network to find me a way to do this linear embedding. I also give a quote here from Stefan Malott. This is I really like this quote because it's very clear. It's the first sentence of his paper on understanding convolutional neural networks. Supervised learning is a high dimensional interpolation problem. The key word here is interpolation. So once you build this, it works for the data you used. And what we know about neural nets is you start to walk outside of that data set. In other words, if you try to extrapolate, most of these models break. So this is very different than most physics models like F equals ma, that if you can take F equals ma and you can use it for planetary motion, you can come to Earth and use it for ballistic trajectories. You can even understand how if two cars crash, what's the resulting, how are these cars going to line up after this crash, because you can use your F equals ma physics. So it's very broad application, whereas neural nets work where the training data was. Okay. Keep that always in mind. But here's what we're going to do for learning these Koopman embeddings. In other words, how can I learn a transformation to a new coordinate system where the dynamics is linear? So here's how it goes. So this is work with Bethany Lush. She's now at Argonne National Labs. And Bethany was just a fantastic student, stayed on as a postdoc for a little bit, where she was one of the, she was the first to train a Koopman operator from neural networks. So what she did is said, let me take my input space, X, let me map myself to a new coordinate, Y. And what do I want to have happen in Y? And by the way, I can come into this, that's the encoder, come out of it back to the original variable, that's the decoder. So I have an encoder-decoder network. And in this space, when I go one snapshot into the future from Y of K to Y of K plus 1, I want that to be a linear operation. Okay, so I'm enforcing this Koopman idea in the latent space representation that I'm building. And of course, you try this on a simple problem, even like the pendulum. You say what I mean by the pendulum, I mean the full nonlinear pendulum, not the linearization of the pendulum. This is theta double dot is sine theta. That's a nonlinear dynamical system. Can I embed that into some linear space? And it turns out you fail. And it took us a while to figure out, but it actually goes all the way back to very simple asymptotic arguments. And it was very clear, obviously, why it failed. I say obviously because it took us a long time to figure that out. I've actually failed a ton with neural network training, by the way. So if you get into neural network training, you should just be prepared to fail a lot. And as long as you're comfortable with that and just failing, and then finally having some success, then that's really good. So here's how it works. This is the Duffing oscillator. This is just a very simple, close to the nonlinear oscillator, which is, it's an oscillator with a small cubic correction. And by the way, here, I scanned in my graduate school notes. So I had written these sometime when I was in grad school. I think it's my second year of grad school. And I decided to scan them in just to show you that, in fact, I did this calculation. And this is well before I ever thought, or most people weren't thinking about neural nets in these days. And what happens if you have a little bit of nonlinearity in your pendulum, right? If you have a correction to the linear pendulum. Well, the nonlinearity does two things. One, it shifts the frequencies, and second, it generates harmonics, okay? And in fact, if you do the asymptotics, here it is. Here is the solution. You can see an epsilon frequency shift. And then at the next order, you get a harmonic here, which is you get the sine of 3 of the angle or of the frequency. So you start generating harmonics, you start shifting the frequency. And in fact, if you draw a spectrogram of this, here it is. This is what you see. As I increase the amplitude of the oscillations, this is what happens. The base frequency starts to shift and you start generating harmonics. Here it is, sine 3 omega, sine 5 omega. And by the way, this shifting frequency, you know about it. If you've ever been on a swing and the rate of pumping has to change as you, like when you're swinging your legs, you're changing your frequency of pumping as you get to have larger and larger amplitude oscillations on that swing. And this is all you're seeing here. The problem with this is, how do you handle that on a neural net? Because if you're going to parameterize this frequency, look at all the frequencies I have to include in this. So when I try to pinch this down into a two-dimensional system, because I know the pendulum is two-dimensional and I want to keep it that way, this frequency shifting is creating problems trying to make me build an infinite dimensional model versus a two-dimensional model. So one way to constrain that is to build a secondary network which parametrizes this frequency shift. And once you have that, then this Koopman operator actually is a 2x2 operator, but it's parametrized by the frequency omega. So this still allows you then to build the right kind of model, and it handles essentially what's called the continuous spectrum of the system. So let's go to so here it is, by the way. This is embedding this thing in a linear space. So this is the nonlinear pendulum. Here's its phase portrait. And you can see, as you get to be large oscillations, you can see the frequency shifts, so longer periods. And also you can see it starts getting deformed from sines and cosines. However, you can learn a mapping to transform this all back into a linear model for all oscillations all the way up to the upright position where the saddle is. And so this allows you to build a linear model for that nonlinear pendulum for quite a broad range of parameter space. And so this is kind of what we're really trying to do with learning a Koopman operator. We can do more complicated examples like flow around the cylinder. So here it is. So if you take snapshots of flow around the cylinder and you look at its low rank projection into some subspace using the singular value decomposition, you find that in fact, it becomes a 3x3 system, nonlinear dynamical system, which then you can embed into a linear dynamical system. So this is fantastic. You take this Navier-Stokes model, which is high dimensional PDE, you embed it in a low rank space, and then you put it also into a linear space. That's quite remarkable what you can do then with this kind of architecture. By the way, those are kind of simpler examples. And we decided to really ramp this up and try to see, can I learn linear embeddings for much more complex spatial temporal systems? And this is work with Craig Jin. And Craig was actually able to do this. This is now out in the European Journal of Applied Math. And you can, by the way, everything I'm showing you here, all the code is up on GitHub, everything, the code, the data, everything. So anybody who wants to reproduce anything I'm talking about, you just download it. It's that easy, okay? And here's what we were doing with this neural network embedding. We were trying to linearize nonlinear PDEs. In other words, can I find coordinate transformations to do this? Now, there's a few PDEs we know about, like Berger's equation that gets linearized with a Kohl-Hopf transform, and also a class of inverse scattering transforms, which allow certain classes of PDEs to be linearized, but it's a very restrictive set. And we went after what's called the Kuramoto-Shibashinsky model, which has complex, chaotic spatial temporal behavior. We thought there was no way in the world you could write down a linear operator for this, but in fact, we learned one. And this is actually, Craig was able to do this. So he was able to learn a linearizing transformation. He set up a much more sophisticated neural network architecture than I showed you previously. But the idea now is that I can build this linear operator in this new space V. And so when I go from V of K to V of K plus 1, in other words, in this new space, I can build a linear map. In fact, right over here on the right, what you're looking at is full simulations of the system. And here's the neural network representation of this. So it does an amazing job of actually capturing this. So I can move into this coordinate system. And since it's a linear operator, if I want to walk this thing way out into the future, it's trivial because all I have to know is the eigenvalues and eigenvectors of that linear operator. And then I can just put any time I want projected onto those eigenfunctions, eigenvalues, and I'm done. Okay, so I don't have to actually solve any computation there. So it's really nice to have linear operators. Okay, so linear models are fantastic because they're easy, right? I mean, you can just write down analytic solutions. But what I want to do is, or one of the things they fail to capture is when you have, in fact, nonlinear dynamics, whether it's chaotic behavior, bifurcations. One of the things that we've developed is this idea of governing equations. Write down some governing equations for some system. You derive them maybe from first principles. Oftentimes they're nonlinear, sometimes they're linear, but nonlinearity produces some really interesting dynamics that's outside of what linear models can produce. So we don't want to restrict ourselves so much to linear models because in some sense they have limited expressibility in terms of dynamic outcomes. So we're going to try to go for governing equations, which allow us a lot of flexibility. So what we're going to build instead is we want to now find a way to say, well, if I'm in this latent variable space, can I construct a model there? And so this is how this SINDy algorithm works. SINDy is sparse identification, nonlinear dynamics, which is I'm going to come in and I'm going to say, suppose there's some model and I don't know what it is, but of course you're seeing it there. It's the Lorenz system. But all I give you is time series data of X, Y, and Z. So I say, here's some time series. Tell me what dynamical system produced it. All this is solving AX equal to B and solving an overdetermined system of equations. That's it. So let me walk you through it. What I'm going to do here is say, well, AX equal to B. What is B? So if I give you X, Y, and Z, time series of that, you can produce for me X dot, Y dot, Z dot. In other words, you can differentiate that data and produce the derivatives in time. Remember, I'm looking for a model X dot equals F of X. I'm trying to discover a dynamic system model. So I have X dot now. It's the B. Okay. The A matrix is a library of potential right-hand side terms. So over here, I don't know if you see me, I'm your little box there. Over there, I got all my, math, engineering, physics books up there. And there's a bunch of different models that people write down for whether it's quantum mechanics, electrodynamics, heat transfer, governing equations. In other words, what are the possibilities of model X dot equals F of X? Well, we've studied these for a long time, and we can build a library of all the kind of things I've seen in these models and put them in here. Okay. So they could be polynomials, cosines, sines, all kinds of behaviors here. In other words, this is just limited by your imagination. I could build a very nice library of potential terms that might exist on the right-hand side of X dot equals F of X. F of X could be any one of these terms. So that's the matrix A, because I can evaluate all of these because you gave me X, Y, and Z, so I could evaluate X and Y and Z and X squared and X, Y. I can evaluate all this library. That's the matrix A. The derivatives of the matrix B. I have AX equal to B. And so now what the X here is, it's essentially the weighting of the library and how it's weighted to represent the solution, the derivatives. But one thing that you could do here, if it's AX equal to B, you could just do backslash, right, in MATLAB or something like this, or least square fitting. And if you do least square fitting, it tries to actually give you a solution where it tries to make all these terms as small as possible, so it spreads them out. And what it does is it says all the terms contribute and to get a regression that works. What we say instead is actually in most physics models, there's usually just only a couple terms that matter. 2, 3, 4. Oftentimes it goes under the words dominant balance physics. But even if when you derive governing equations like Schrodinger, it's 2 terms on the right-hand side. Navier-Stokes, 2, 3 terms on the right-hand side. So all these canonical models of physics and engineering have very few terms. And so what we're going to say is, okay, find me a model with only a few terms. So instead of using a least square regression, use a sparse regression. In other words, try to find me the weights that are as sparse as possible to make this work. And so that's exactly what we do. So you can imagine this as being something like a lasso, AX equal to B, but lasso is awful. It's really a bad L1 regressor, by the way, and that's my opinion. So we developed a sequential least square thresholding to promote sparsity, which is much more stable. And in doing so, you give them the time series, and then when you do this regression, it says, here's your model, and it gives you actually back the dynamics that produced it. So you discover the governing equations right out of the data itself. You can take this and modify it to spatial temporal systems. So this is work with Sam Rudy. Sam did it for PDEs, partial differential equations, right? So he did KDV, Berger, Schrodinger, NLS. So you take all these data streams. So all you have is space-time data. And from these, you can discover the form of the governing equation, okay? And what we have over here is sort of what we use to discretize it and how much noise you can handle. A lot of this works well, provided you have pretty good derivative estimates. And as soon as you start putting noise in the system, you need better ways to differentiate your data. You can't just use finite differences because it's just too blunt of an instrument for this. You really need to use like total variation, some smoothing. And that's one way. And we've worked, by the way, very hard at making this more stable and robust to noise. And we've come a long way since the original works in 2016 and 17. So this gives us a way to discover governing equations. But it turns out, for the most part, in many cases, we already know some physics, right? So it's interesting. So you can say, the idea that you come to a problem and you know nothing is also a little bit maybe fake, okay? So what about, by the way, someone asked, what about higher order finite differences? Still doesn't work that well. It works better than, second order. Higher order, you get better, but we've moved almost completely away from doing differentiation with finite differences. It just kind of sucks. All right. So we're going to get to this idea of discrepancy models. So the idea is, I'm not going to start off with the idea that I have no knowledge of the system. In fact, oftentimes I have some knowledge of the system. Maybe I know the Hamiltonian or Lagrangian or constraints, or I have some partial knowledge of this system. So in other words, when I come to it, I know, for instance, my imperfect model, I know this at some f of x, this f of x, I derived it maybe even. So I know this is there. The problem is my model is not good enough to explain the data. I'm missing physics. So this is a discrepancy. That's the missing physics. So notice this SINDy platform is super flexible. You can just take this known physics, f of x, move it to the left. And so remember the vector b, which is the derivatives. Now it's the derivatives minus f of x. Now you just do your SINDy regression then. It's really trivial to integrate prior knowledge into this. Now, why is this important? Because models like this is a double pendulum on a cart. And in the top one, the model is such that what it has is knowledge of the perfect physics. In other words, there is no frictional forces anywhere. And if it has this perfect model of physics without the actual physics, what you see happens is this cart has knowledge of that perfect physics and is unable to stabilize it in the upright position. In contrast, if in the bottom, you give the ability of this thing to see the data, see its model, look at the difference and start building a better model, in other words, building the discrepancy, now you get yourself in a position where it's learned the missing physics to be able to do the trick you want it to. Why is this important? Because I think this really highlights where we're going as a community with this idea of the digital twin. So the digital twin concept right here, which is I have a robot arm and I have a CAD-based simulation of this robot arm. And what I'd love to do is put a bunch of these together and sort of, in some sense, do a simulation of my factory floor, for instance. But it turns out this model here, which is a Platonic model, in other words, it's perfect physics. If you're doing precision manufacturing, this is not accurate enough to actually capture what's going on in that real robot. You have sticking of the joints, and every time you oil it, you get a different discrepancy model. Every single robot arm has a different discrepancy. So you can imagine using this framework to say, if I want to improve this, I would take the difference in the models and build a better model in my CAD-based simulation by learning the discrepancies. Think of this as a very smart Koopman filter, right? Koopman filter takes data, takes a model, and tries to do the best job in predicting. The one problem with Koopman is you always look at the discrepancy and it never learns to say like, well, I'm always making the same mistake. Maybe I should just build a better model. This is exactly what this does. Takes the difference over time, says, here's the better model. I close the gap between my data and my model by doing this. Okay, so by the way, this architecture of governing equations is all kinds of, it's very flexible, modular, adaptive. And so there's a bunch of different ways to start, take it. You can learn parametric representation of dynamics. You can do control with it, hybrid systems, low data limits. You can coarse grain things, do boundary value problems, stochastic systems. You can put constraints on it pretty trivially, and even look at point array maps, point array flow. So it's such a simple architecture that it allows all these build-ons that you can do, which is something that's really nice as a base model. Okay, by the way, one thing I swept under the rug there is I didn't really discover coordinates. I assumed I had the right coordinates to begin with. And this is where this work with Kathleen Champion, who just graduated about a year and a half ago, Kathleen did something that I think was very important, which was she went to this thing to say, look, if I take data from a system and I actually don't know what the right coordinate system is, this is where I started talking about it, that we start saying, I need to learn a coordinate system and the dynamics. What she did is brought the two together. We had the maturing of SINDy, this in other words, model discovery, and then learning coordinate embeddings, which I talked about in the Koopman section, or the linear method section. But now we're going to bring them together. And what we're going to do is learn a coordinate transformation, not to build a linear model, but to learn a parsimonious representation of dynamics. Here's the loss function. I mean, you just set up this architecture. This is your loss function, go. And what this thing is pretty remarkable, because it gets us to the point where we can start doing what I like to call GoPro physics, which is, suppose I film a pendulum. If you film a pendulum, of course, we're totally biased. We see the pendulum, we know that, oh, the theta to theta dot coordinate system, we can just look at the video and see what the right coordinates are. But if it's just a camera, all it sees is pixel space. So pixel space would be here, the input layer. It has to learn theta theta dot. And then it has to learn from those that theta double dot is sine theta. That's the process. Can it do it? In fact, Kathleen was able to train it to do that. So there's a very simple examples here, but really the nonlinear pendulum is right here. It can take videos of the pendulum, learn a transformation. It learns theta theta dot. It learns that critical coordinate system and then learns the dynamics in it. What we'd love to do with this is do planetary motion, right? The problem is getting enough good data there. But think about this. That was the whole thing I started with. If you see the retrograde motion in the sky of these planets, what do you have to learn? You have to learn the right coordinate system, which is the heliocentric world. And then you have to learn F equals ma. This is exactly what this is getting after. Learn a coordinate system in which the dynamics representation is really parsimonious and interpretable. And that's what she was able to do with this. Interesting concepts here. The actual neural network, in other words, a coordinate system, is not generalizable. In other words, if I take my coordinate system learned from Mars, it doesn't work for Venus. But the physics models that I get, the F equals ma piece, is generalizable. That model holds for all the planets, even though each planet individually needs its own coordinate system. Okay? So this is still a nice way to play with things, is once you've discovered some physics, you can now lock in the physics into this middle layer and then just learn new coordinate systems with much less data if you move to a new system. So that's kind of the concept. So notice that for the most part, I've been spending a lot of time about thinking about learning spatial transformations. How do I transform coordinates so that now I get these nice time models? I could just work directly with the time coordinates themselves to transform it. So this is work with Henning-Lange. In a nutshell, here's what it does. You give me some complicated time series data. Look, and if I were to take this thing and Fourier transform it, it'd be a ton of modes because I have these sharp structures. But if I were to train a neural net to try to embed this into a minimal set of sines and cosines, in other words, warp this thing so it looks sinusoidal, that's actually pretty easy to do. And once you've done that and you have a minimal set of sines and cosines, then it's fantastic for doing long-term forecasting, mid-range forecasting. In fact, this little trick, right, which is learn a neural network right here, this f of theta, where you embed things in terms of sines and cosines, is remarkable on long-range forecasting. By the way, here's an example from Power Grid. And we did this Koopman forecasting, and here's the error that you get. And I want you to notice that what we did is we compared it against modern, the top level time series prediction methods, LSTMs, GRU, equistate networks, also against statistical methods for time series analysis, things like ARIMA and so forth. And this thing just beats all of them. So in other words, you should also walk away, hopefully, from this knowing that, like, just you threw it into a neural network doesn't mean you're going to beat everybody. The LSTMs and GRUs and equistate are great for a little delta T step, but what we're doing here is long range forecasting, right? So if I want to predict way into the future, the best functions you have available to do that for you are sines and cosines. And the best way to get the best sine and cosine representation is by training a neural net that takes your time series and tries to warp that time series into really nice small number of sines and cosines. And then you get this fantastic prediction. And that's exactly what Henning did. This kind of architecture can build us much better reduced order models. And so here is, for instance, a PDE simulation of a full simulation versus here what we do is we look at a reduced space by just taking the SVD, looking at the time series, and then just basically taking that time series, doing this training to do the long range forecasting, this Koopman forecasting. And now I'm not even solving a PDE anymore. I'm just saying, here's the future state. I have a linear model, a Koopman model, and I can give you the future state. And this is incredibly accurate and it's very stable, unlike most reduced order modeling paradigms. Okay. By the way, you can continue on this idea of neural nets for thinking about time, and you can even build really interesting neural networks for understanding flow maps. And this is work with Yu-Ying Liu. And Yu-Ling basically said, hey, look, a lot of the physics systems that we look at, I don't know what kind of problems you guys look at, but the ones we look at often have multiple scale and time and space structures. So one of the things we were looking at is, like, how do we do a better job of doing multi-scale physics? I think that's a challenge for the community in general. So what Yu-Ying did, he said, okay, look, here's the thing we're going to do is we're going to start learning flow maps. We're going to say, look, this is normally how you would write down a numerical stepper. The solution in the future is some, F of the solution now, which would be like a Runge-Kutz scheme. But here what we're going to do is learn a neural network that takes me from some time to the next delta T. But what we're going to do is we're going to learn small steps, delta T, medium steps, and big steps. So we're going to say, how do I march long ways out into the future? And I'm going to take input-output training pairs to do that. So what I can do if I want to go out long into the future is I can take some really big steps, like this green one here, to get way out into the future, then refine my step with the medium and the small steps. And this is a fantastic way. It's quite remarkably accurate, compared to like standard numerical stepping, which always requires you to resolve essentially the fastest time scale. Here, we do resolve the fastest time scale with one neural net, but then we can take big macro scale steps into the future with this slow step. And so this is a really nice framework for thinking about things. By the way, let's also compare it. Here are some different things we compared it on. So we took some spatial temporal system, which is Kurmo-Shevchinski. We took as well, we did some models here, which is, music, flow around a cylinder, and a video. And we just said, take this thing and basically predict the future. And so here's our method. And you can see we did a really great job with this. LSTMs, they suffer quite a bit. ESN, these are all different neural network approaches that you might take. But this multi-scale stepper really divides up the problem in a way that's very natural, which is to pull out the multi-scale features. This is why wavelets are so practical and important, is because wavelet decompositions pull out scales and allow you to represent things in a very nice multi-scale way. We do this here, and again, this hierarchical stepper has a natural representation that you can take advantage of. Oops. Okay, also Yu-Ying did some multi-scale physics. That was multi-scale in time. He also developed to do multi-scale in space, which was essentially what we've done for a long time is built multi-grid methods. We solve some PDE, and wherever we have sharp gradients or a lot of structure happening, we resolve our mesh around these areas. And you could do the same thing with neural nets, which is you can train some neural network to catch some coarse grained behavior and figure out where your error is largest. And then you build neural networks that would now, like a convolutional structure that looks just where the error is large, you refine in those areas, and you use transfer learning to take your coarse grain, move it to the next level, train that next level of resolution, the next level of resolution, and so forth. So this is a really nice way to sort of exploit these concepts of transfer learning and also multi-grid physics methods. Finally, I'm going to close off with just a couple examples here from boundary value problems. Everything I've talked about so far is temporally dependent, but boundary value problems are prevalent across engineering and physics. And so we've started thinking about that quite a bit. And it's very much the same architecture we've been thinking about, except for now, your input data, you're trying to figure out a coordinate transformation into some other representation of, can I learn a boundary value problem? In other words, if I take data from a boundary value problem, could I learn the governing equations of that? So it's the same kind of idea that we have here, which is take this SINDy type architecture and learn this coordinate transformation. Oh, by the way, the other thing I'll just say is that we also recently modified this to say, can I learn a coordinate transformation to make my boundary value problem linear? And then I can build Green's functions in there. So we call that deep green, which is you can sort of say, take this architecture and make, and essentially learn Green's functions nonlinear Green's functions representation by being able to map in and out of a space where linear superposition holds. All right, so this is me wrapping up then. I think this is probably a good time to wrap up. Good, I could take some questions too. So the conclusion, at least, this is just one perspective for people, right? For us, this is, so, you shouldn't take any of this too seriously. Everybody's going to have a different opinion about how they like to do their physics or what they think is important in neural nets. But for us, where we've been concentrating on effort is this basic problem. Take measurements, try to reconstruct physics. And the way we're doing this, the number one regularizer in all of that I talked about was to say, this F here, I want that F to be a parsimonious model. We have made amazing progress in physics by having nice representations, Maxwell's equation, Schrodinger equation, Navier-Stokes. We've advanced technologies beyond our dreams, partly because those equations, once you have them, allow you the flexibility of extrapolation. So for us, at least for our objective function, that's important. And that's, you see throughout this talk, that's what we are really bringing in to take this ill-posed problem and make it well-posed. Well, in there. Thank you, guys.
Yeah, thanks again for your interesting talk. And we have some time for questions. Okay,
Perfect.
we have one question from Anusha. We recently tried Champion's method on a system where there were a lot of statistic variables, not just dynamic ones, and struggled some. Any suggestions on how to use with static variables?
It's a good question. I'd have to look a little bit more carefully at what you're doing here. So obviously it sounds to me like you have a hybrid, you have some dynamic variables and static variables. So the static variables, I'm wondering if they're boundary value problems or constrained in some way. Maybe if I knew more about your system, we can always chat offline on that at some point if you want to send me an email. But one of the problems with, by the way, I'll just say this, one of the problems with some of these methods, like one of the things that we didn't integrate fully into Champion's method was our noise filtering thing. So I've already said this, and let me just say it again. A lot of this depends on getting good derivative estimates, right? So if you're going to build dynamic models, right, it's x dot equals f of x. And if you can't approximate x dot well, it really is difficult to develop good models if you have a terrible estimate of x dot. Now, we've developed a lot of techniques for trying to pull out a good clean x dot. But in Champion's method, we never put any of those in. So the Champion method is sort of just with pretty clean data. So it could be that you're just getting breakdown also just because we didn't put any of the denoising tricks on it.
Yeah, thanks, Nathan. This is Anusha. I'm a UW grad, by the way, so I've met you before. Yeah, our system was actually pretty clean, but I think what was happening was we had a lot of the static variables. Very few of our things were dynamic, features were dynamic. So even with the autoencoder, we were not able to reduce it to a good enough linear system. I think we just had a lot of, the whole matrix was not very well invertible. So just wondering.
You often get this issue of having, I mean, the matrix, the library matrix is typically terribly ill-conditioned. And it could be that with the static variables, it's so ill-conditioned that it makes it problematic. Are the static variables relationships between variables?
Yeah, well, they are.
Okay.
You can think of it as if in the pendulum problem, if you had the length of the pendulum as one of your variables, for instance, right?
I see.
Yeah.
Right. Okay. Yeah. So there could be a way also to then place these in as constraints. That's another possibility, is to do this. So one thing that SINDy allows you to do is very easily place constraints on when you do the regression to this x dot equals library theta c. Is sometimes you can also say subject to, and then you can place constraints on that. So there's this paper by J.C. Lazois and Steve where, it's just AX equal to B, but now it's a subject to line in that optimization, which I think you could easily do here with the autoencoder as an extra constraint on the regression.
Okay, so think of it more of a constraint rather than a feature. Okay.
Yeah, that might work out for you. Yeah.
Okay, thanks. And I had one. Okay, sorry. Do you have another? I was going to ask one more question, Patrick, if I may, or I can wait.
Can you wait, because we have two other people, and then we could ask you again?
Sure, thanks.
Okay, so Peter has a question, and I will allow to talk so he can ask his question. So please, Peter, go ahead.
Yeah, thank you. What a great talk.
Thanks, Peter.
I actually got my PhD from University of Washington from Terry Rockefeller, so he was in.
Oh wow! Okay, yeah.
Terry's still doing well. I guess he's almost 90 years old, but we still keep in contact.
He's kind of an amazing guy, right?
Sure. What I was kind of curious about, so you have a dynamic equation, but you really are not trying to influence it through control. Now I understand that you're reading from data, but do you think that there's a additional issues that you can put in there, put an optimal control problem, which you can influence the data as you play it out? I'm not sure this is a good question or not. The talk was so wonderful; it's hard to.
Yeah, no, we've played around this with a little bit. We've been actually looking at taking, for instance, this top line here, f of x plus, let's say plus bu. Let's make it. Sure. Yeah, let's make it something we might be able to actually handle, right? Which is, I have an actuation system kicking this.
Okay, well,
could I discover this?
And could I about a running cost or a Lagrangian as a running cost?
Yeah. I mean, we've definitely played around with control. I don't think we're as far as we would like to be with it, but it's something that can actually really be brought into here. In fact, we have a recent article up in the archive that sort of gives a little bit of sort of an overview of sort of different methods to sort of integrate with SINDy. We call it SINDy with control. And part of it is, to your point, right? Like if you're going to discover dynamics, it's problematic if there's actuation signals just pounding this thing, right? And you haven't identified them, because what you're going to do is say, oh, that's dynamics. It's like, that's not dynamics. That's actuation. And if I can separate them, I can actually get the physics disambiguated from the actuation. So I think that's something we're definitely looking at.
That's really fascinating. I found this to be an incredible talk. I teach a course here and trying to teach undergraduates some deep learning, and we're reading Strang's book and having some fun with that. But boy, this is wonderful. I really love this. Thank you very much.
Great. You're welcome. Thanks, Peter.
So we have a question from Steve. I will allow him to talk so he can ask his question. So Steve, please go ahead.
Yeah, so I noticed that a lot of these examples you've been showing us are fairly simple physics, but I'm wondering if you've ever thought about applying this to general relativity.
Oh, we have. Actually, we've been wanting to do gravitation in general. First of all, like that picture I showed at the beginning, right? There's a, let me just bring it back here and share screen. Shoot, let me bring it. Okay, sorry. If I go back, like I actually want to apply this Kathleen's method. Sorry. I hate when people do this, but I just did it. Anyway, right to this, for instance. Imagine that is my data. So I would love to, these are your snapshots from the night sky. You're going to use, the size of this ball is going to be some proxy for distance, and then that's the pathway. Could you, from this data, actually pull out the heliocentric coordinate system and the F equals ma, right? The inverse gravitational law. And this is actually where we want to go. I have one of my students working on this now. And part of the reason I'm actually thinking that we might be able to finally do it is we've now framed this whole SINDy regression in a Bayesian framework, which allows us to have do this with a lot less data. Because look how many data points you actually have here. It's very few, right? So you really got to okay, maybe you could collect a lot more. We just don't have it. But I think we can do something like this, and we would love to have data where there is GR effects, where we could actually do this regression and say, what does this thing pull out for you? Can it actually discover GR?
So one of the things I'm thinking about, since I work in GR, sort of, kind of, in general relativity, we've gotten to the point now where we can do simulations of black hole collisions on meshes and so forth, and it's you wind up with like 100, some number of 100 variables per grid point, and you're doing stepping, and most of us use finite differencing at the 8th order. But where the problem comes in, we can do quite well if we have two black holes that are approximately equal in mass, and we can do quite well if the black hole mass ratio is near infinity, right? But the problem is in between. And the difficulty that's encountered is all our methods are stuck evolving at the speed dictated by the smaller black hole.
Oh, yeah. So in other words, it's basically, to resolve that, I suppose you have to have your timing steps based on.
Yeah, and so that makes, like, if you have a ratio of 100 to 1, it's just prohibitive. You just can't do it. And I was looking at your picture where you're leapfrogging over time steps.
Yeah.
Thinking, wouldn't it be nice if we could wave that magic wand on that intermediate mass ratio problem?
Yeah, in fact, that's actually a very interesting idea, because I think that's exactly where this methodology could work, right? I mean, I think we've been really pleasantly surprised at how amazingly well this works. Like I said, this is the comparison, right? I mean, we can walk way out, like, you take on big steps the stuff that's happening on big steps, and then you resolve the fine scale stuff. And then once you've learned these flow maps, you just put them together. It's really amazing. And something like this might allow you then to sort of say, look, I've got these flow maps built, right? So obviously this requires training data. So you're going to have some high fidelity data to build these maps, right? So there's that initial cost of like, well, I have to do some of these really fine scale data and just pay the cost of making sure I resolve that smaller black hole versus the big one. But once I get some training data, then you could do more simulations now very quickly with some architecture like this.
Right. That's what I think. That's what it looks to me like. There's a possibility for doing. Now there is. Well, as I said, most of the codes are finite differencing. There is one code that does spectral methods, and maybe that one would work better for you.
Yeah.
But it seems to me like if you're looking at things to point this at, that's one possibility.
Yeah. Oh, okay. That sounds great. Yeah, you should send me. You put in a link, or I would love to know where to follow up on that. That sounds like super interesting.
I'll put my email in the chat.
All right.
Okay, I think we have one more question from Eric. And he's asking, can this method be applied to systems described by differential algebraic equations as well?
Yeah, so some people have done this where you can regress to, again, you can build a library. You have to set up that regression, but again, you could say, you could set up the regression to say, what I want to look for is essentially relationships among the variables, right? So they're not time dynamics. The interesting thing here is, in some sense, now you're looking for a sparse way to represent a null space. So normally on the left-hand side, you have x dot equals the map of x. Now you have algebraic relationships, which are a set of, generically some set of relationships equal to 0 on the right-hand side. So the only problem with this is that oftentimes when you look at sparse vectors in a null space, you need exceptionally clean data to do this, because the null space it's really hard to get a sparse null space spanning. We've done this before, and we found that the sensitivity to noise was just really brutal on us. So if you have clean data, you could do it. If you have noisier data, I don't know how to regularize that very well. There might be some extra tricks we just haven't done them, right? We haven't developed in that direction.
Okay. I think we have time for one more question. So for the champion paper in the nonlinear pendulum, it looks like you give the neural network not just images of x, but also dx/dt and d squared x/dt squared. Isn't it somehow cheating to give the network such information? We normally don't have acceleration.
What we do is we have the video, and from the video, you can compute a gradient. So, right, so what you have is snapshots, right? So you say, I have the picture of the pendulum at t plus delta t plus 2 delta t. Then you can compute the gradient from that. So that's not cheating. And then you can compute a second derivative from that as well. So what you have, though, are the snapshots. That's the only assumption we make, is that you have the video and you have timeframes of the video, right? And then you can compute all of these quantities that we use in the regression. In other words, we don't assume that we have any other data than just the picture over time. So this is why computing derivatives becomes really important, right? Because if the only thing you have are those snapshots, if you don't compute clean gradients, or clean derivatives, it's really difficult to model build off bad derivatives. Because another way to think about everything I talked about with that stuff was, it's just a regression onto derivatives, right? And so if your derivatives are bad, then you're in trouble.
Okay, so one last question we ask to all speakers is, because this colloquium brings together people from HPC, high performance computing, and deep learning, and so on. So what do you think are the major challenges for the HPC folk to improve these methods, and what are you using from the HPC folk, or what do you wish from the HPC folk to accelerate these methods or something?
That's a great question. One of the things that you see here, and often that's swept under the rug with deep learning, is we just assume we have this data, right? And Steve was just asking about, like, okay, I have these black holes colliding, one big, one small. I'm already in a really difficult spot. But you're not going to be able to build a model unless you initially have the ability to create some very high fidelity models for us to train deep learning on. So there's no way to get around the fact that we still need the HPC. Now, my training is actually on GPUs, so maybe, right, there's now more effort toward building, big clusters of GPUs, but you still need to just do the forward simulation to produce the data. That's just like, there's no way around it. You can't build a model without the data. And by the way, one of the interesting things that's happening, right, for the community is the success stories that we talk about, whether it's language or computer vision. What we don't talk about is the cost, what the cost was to achieve those, right? So your best language models, right, they train for 6 months on hundreds or thousands of GPUs, and just the cost of electricity is $600,000, right? So, for us as academics, we can't do that. Right? But if we want to start going to big scale problems, at some point we have to act like Google or Facebook. We have to say, if I want to understand, if I want to build some of these deep learning models for, understanding black holes, I'm going to have to still do these really huge simulations in order for me down the road to pull out models that now I can do very simply potentially, or much quicker. But there's still that upfront cost that's going to be always there for us, I think. So HP still in the game, will always be in the game. So, yeah.
Okay, thank you so much for your talk and for the discussion. It was quite interesting. And yeah, hope to see you next month when we have George Kardinakis, and he will talk about physics-informed deep learning in the next seminar. Okay,
Thank you guys
so
for
much,
having
Nathan.
me. Stay safe, guys.